In the last video, we saw that if you have an aldehyde in solution and there's a catalytic amount of aqueous base, then the aldehydes will start sticking together and creating aldols, beta-hydroxyaldehydes. So we discussed that in detail in the previous video. In this video, we want to think about that reaction that we first learned about last time from the perspective of synthesis. Now the base is going to steal a hydrogen from the alpha carbon. The alpha carbon will turn into a nucleophile and attack the carbonyl carbon electrophile of another aldehyde or ketone. You can draw the mechanism, and it's worth thinking about, where you have the alpha carbon losing its hydrogen, becoming a nucleophile, attacking the carbonyl, and then you just protonate what was the second carbonyl oxygen to stabilize it, to give you the beta-hydroxyaldehyde or ketone. You could draw that whole mechanism out. In this video, I'm going to help you out a little bit by giving you a sort of shortcut for drawing the products of these things. So take the original molecule. We're going to draw that molecule again a second time, because these things are reacting with other versions of themselves. But where the oxygen is, replace that with the alpha carbon. So that oxygen, I'm going to have the double bond going down, so I'm copying that double bond. Then we have a hydrogen on one side, so I'm copying that. And to the left, we have 1, 2 carbons. So 1, 2 carbons. And then the 6-membered ring with another down here. So 1, 2, oops. So this is the carbonyl carbon. We have 2 carbons to the side, 1, 2. And now we just need the ring, which is another carbon. And so that's our first step in drawing this. And it helps to number. So you have 1 is the carbonyl, so 1, 2, 2, that's the alpha carbon, 3, 3, and then you have the ring carbon, which is 4 here. Okay, that's the first step. The second step is erase the second step is on the beta carbon. So remember that the alpha carbon is the one next to the carbonyl. The beta carbon is the one after that. On the beta carbon, add an OH. And lastly, erase the double bond. And that is the product of the aldol addition. Remember that in an aldol addition, you get a beta-hydroxyaldehyde or ketone. So alpha, beta-hydroxyaldehyde or ketone. So that's why we drew that OH on the beta carbon, and otherwise the second molecule should be exactly the same. This beta carbon was the carbonyl carbon of a second molecule that got attacked by the alpha carbon when it became a nucleophile, as we saw in the previous video. Okay, and you can erase this hydrogen at the end if you want, because that's implied in the skeletal structures. Okay, let's try it with B. So you look at your molecule, we're going to attach things to the alpha carbon. That's what turns into the nucleophile and attacks the carbonyl carbon electrophile of another version of this molecule. So where the oxygen is, that's where the alpha carbon is going to be. Below it, we have a double bond. To the right, we have a bond to a hydrogen. Okay, now let's number this. To the left, so here's our carbon number 1. We're going to have 1 more. It's carbon number 2. And then we get this ring as on carbon number 3, starting on carbon number 3. So you'd have, okay, this is carbon number 3. The 5-membered ring attaches to that. So there it is. All right. So now that we've sort of redrawn this molecule, just instead of the oxygen, we have the alpha carbon. Now, and I strongly encourage you to number it so things don't get confused. It's very easy to draw the wrong number of carbons here. And in that case, you would lose a significant amount of points because the implication is that somehow the reaction would get rid of the carbons, whereas it definitely does not. After you number those, I would encourage you to maybe erase the numbers and draw in the Greek letters. So the alpha carbon is here, the beta carbon is on the other side of the pi bond. On the beta carbon, draw an OH. You always, with these aldol additions, you always have a beta hydroxy aldehyde or ketone. And then last, erase the pi bond between the alpha and beta carbons. You can also erase the hydrogen that's implied in the skeletal structures. And so, this is the product you would end up with. The alpha carbon acted as a nucleophile and attacked what was the carbonyl carbon here, kicked the pi bond up, and then that oxygen got protonated. So that would be the aldol from that reaction that you would get if you treated the original thing with some aqueous sodium hydroxide. Okay, let's try it with C. So in this one, you look at the carbonyl carbon, and then look over to the alpha carbon. That's the one that's going to be taking the place of the oxygen in this next molecule that we draw attached. All right, now first, and this looks really weird, but let's just draw the double bond there. That's what's below that oxygen. To the right, we have a bond to a hydrogen. And to the left, we have a 6-membered ring immediately. So there is our 6-membered ring. And if you want to be sure, you can always number it. So here's 1 and then 2. This was the carbonyl carbon and then 2. Okay, now that you have that second carbon chain attached, instead erase the numbers and redraw the Greek letters. So this is the alpha carbon, and then crossing the double bond you have this beta carbon. On the beta carbon of the double bond, add in an OH. With this aldol addition reaction, you always get a beta hydroxy aldehyde or ketone. So you always want to put an OH, a hydroxy group, on the beta carbon. Now, finally, erase the pi bond. You can also erase the hydrogen, which is implied, and if you want, the alpha and the beta. And that leaves you with your final product. So this alpha carbon was deprotonated by the base. So this happens in aqueous sodium hydroxide. Deprotonated by the base, that attacked the carbonyl carbon of another version of this molecule, kicked the pi bond open, and the electrons stole a hydrogen from water. That's how that got protonated. So that would be the aldol product of this aldol addition reaction. Okay, let's apply it to D. So in this example, this alpha carbon is going to take the place of the oxygen in a second version of the molecule. So on this alpha carbon, we can draw a double bond. That's like this double bond here. I know it looks weird. This is just a rough draft. We're going to clean it up later. And here, let me just do this. So we have that double bond. And then the carbon at the other end of it is carbon number 1. We have carbon number 2. On carbon number 2, we have a methyl branch in one direction. So that would be like carbon number 3. And then an ethyl branch in the other direction, off of carbon number 2. So that would be like 4 and 5. So 4 and 5. Okay, so once you have all of the carbons attached, now erase the numbers and write in the Greek letters. This is the alpha carbon, and then follow the double bond to the other end. You'll have your beta carbon there. On the beta carbon, draw in an OH. With the aldol addition, you always get a beta hydroxy aldehyde or ketone. Finally, erase the pi bond. You could also erase the Greek letters, and that is your product. That is the aldol addition. That's the beta hydroxyaldehyde that you would get if you had catalytic base in a mixture of this original aldehyde. The alpha carbon would have a hydrogen ripped off, it would turn into a nucleophile. That nucleophile would attack the carbonyl carbon of the second version of this molecule, break the pi bond to the oxygen. The oxygen with the negative charge would steal hydrogen from water and become an alcohol. Okay, so you can see that predicting the product of these aldol, because these products sometimes look kind of weird, predicting the product is a skill in and of itself. Remembering how the reaction works is important. We talked about that in the previous video. But predicting the product is also a separate skill that needs requires some practice. But the general procedure is redraw the same molecule, but where the oxygen is, have the alpha carbon of the original molecule. Then, and make sure you number your carbons so that you don't lose any, or you don't add any. You have the same number. Then erase the numbers, write in the alpha and beta, where the beta is going to the other end of the pi bond. Add an OH at the beta carbon, and then erase the pi bond. And that should give you your aldol addition product.